Welcome, everybody. Thanks for joining us here on Claims Corner. We are coming to you live. I believe this is our fourth season.
Yep.
Is that right?
Yep.
What episode are we on?
Episode 6.
6.
It's been a while.
Wow.
It's been a while.
Yeah, thanks for being here. This guy next to me, of course, for those of you that don't know me, I'm David James, property training manager here at CNC. Murphy, you want to introduce yourself?
Yeah, my name is Murphy Buggs. I'm also in the training department as well. Co-hosting for the third time now. Super excited about it. Appreciate you having me. I always love being on these. I used to always be a listener, but now being a host is that much better.
That's right. Glad to have you.
Yeah.
So
Third time host,
so
first time, long time listener, third time host.
That's right.
Are we?
That's right.
I swear we've been hacked. Is there
We
somebody
have a heckler in the crowd. Can we
What is
can
going
we
on?
boot him?
Yeah. So if you wanna, you're gonna introduce me real quick. I'm Craig Fowler. No, unfortunately, I'm not in the booth with these guys today. They actually said, "Hey, we got this. We're gonna kick you out. You can't be here." And I got our producer guy Jeremiah. Like, you need to send me a link. I can't resist. I mean, it's such a good topic, such good information. So here I am. I'll be the silent heckler.
What's that behind you? Did you paint your room? Put some
My
lights
office.
up there for break. Okay. All right.
Since Craig is here, we'll have to can the idea of we were going to do a mock draft today instead, but since it's draft day, so Craig's here, we'll do that next time.
Still got Bryce Young going first, though, right?
Sure. Yeah.
Today's topic is earthquake damage. Is it or isn't it? It's going to come up. Craig, I think you actually predicted this last episode that with all the stuff going out on the west coast about earthquakes, never know when it's going to happen, right?
Yeah, I mean, just with that snow melts, there's just I don't know. You with all the amount of snow that's had the melts happening, it's going to start causing causing flooding. I just have this feeling it's just going to result in some type of earth movement, earthquake. It just, it's one of those things where the fault lines just now are going to be saturated. The whole area is saturated. And it hasn't experienced that type of. Speaking of California, it hasn't experienced that type of saturation before. And I just had, it's just one of those things you go, okay, we need, we've been working on refreshing our California earthquake or earthquake training, putting all that back on the CNC Pro, having that ready to go. And I was like, this is a great topic right now to get somebody involved that can talk about what we see, what we're looking for, and then getting the engineer involved. When do we get the engineer involved? How do we get them involved? So yeah, it's just a hot topic right now for me.
Right.
It's a shaky topic. Let's put it that way.
There you go. There you go.
Right. So before we get into we've got an expert with us, Keystone Engineering. Before we get into that, we just wanted to talk about a couple of things. Earthquake damage from the perspective of an adjuster.
Yeah.
What we might encounter when we go out there, when we get the claim, and you're out there and it's like, do I need an expert?
Do I need an expert? Yeah.
Right. The damages from earthquakes are unique, of course. There's a combination of things that could come into play.
Yeah.
When you got that, you've got the soil makeup. The intensity of the earthquake, the type of foundation, really the design of the building as well.
Yep.
Comes into play.
Absolutely.
So lots of factors to come in. When we're working these claims, the beginning of our scope when we get out there, obviously we're going to look around, take a visual observation. After that point, if we feel like we need one to be involved, we need to do that immediately, right?
Yeah, absolutely.
Of course, we want to make sure everything's safe. Does it have access to the home or to the location, the lost location?
I think that's a battle that you have to face right off the bat. You think earthquake, it's not like your wind damage, where you can always just go right out to the house. Earthquake damage, you don't know the extraneous factors around it that are not going to let you be able to get out there and inspect. So, yeah, that's absolutely correct.
Gas lines, power lines down, not functioning. Of course, you want to make it safe for everyone. Notify those that need to be notified.
Yeah, I mean, you look at the photo there on the right. I mean, just that roadway, that's that's an access point to wherever you're going to be inspecting. You never. It's not just that one house or that one building that's been affected. There, odds are there's a lot around it that's been affected.
Right. Going into obvious damage versus what may be questionable, and really the key is identifying the need, being timely to do that. Jeremiah, can we go to our next slide? One of the more common places when we run into or when we come across is concrete.
Absolutely.
Right? Concrete. So when we come across this, we're looking at things to look for. When you're looking at that is, is it fresh?
Yeah.
Is there any type of debris, anything that may have built up over time compared to being sudden and accidental, of course. Any type of sloping, is it sagging? Any type of ground failure around you, maybe a key component or collateral, to look for. When we're looking at these types of things, which I think you're going to touch on here in just a second with the photos, but don't forget about slab on grade. They may have brittle stuff like slate tile, ceramic tile.
Yep.
That may present itself. Stem walls, cripple walls. I want to look in those areas to kind of help you. If not, get a start. Build a case for it.
Yeah, I mean, you look at those two images there. Can we go back to, the two images there? I mean, just the shape and the cracks, I mean, the T-shaped crack typically the result of some kind of a shrinkage, whereas that X-shaped crack is really a telltale sign, a dead giveaway that there's been some kind of, earth movement that's been back and forth that obviously would resemble earthquake effects. So that's always another thing to look at. And again, like David said in his first point there, more in your concrete surfaces, ceramic tiles, things like that. So
yeah, that T-shape. Result of shrinkage. That's expansion and contraction.
Right.
So go to our next slide there. I was about to call you Murphy, Jeremiah.
Yeah, so this slide here, I didn't mean to interrupt you. This slide really here is going to talk about, when do you use an expert? When are certain scenarios, and there's a lot of bullet points on this slide. We won't go through each one of them, but just a plug here. A lot of this is in our earthquake certification course that we currently have and are continuing to develop. I know we're making some tweaks to it, and we'll be republishing it on CNC Pro.
Why is that? Because we can't just have one set. I mean, things change. The industry changes.
No, absolutely.
Year in and year out, we want to refresh it.
Yeah, I mean, the CEA, California Earthquake Association, yeah, I mean, they're constantly making changes as well. So we want to make sure that our training is constantly up to date. It's got all the correct information in there and the most, again, up to date, the newest guidelines in there. So those are some things that are being tweaked, and that will obviously still be published on CNC Pro. Obviously, we encourage everybody to take a look at that. But back to the slide, when do we use an expert? One of the main reasons is when a building is partially or fully collapsed. I know we talked about that a couple slides ago, but that's typically when you need to get an expert. I mean, you think about strictly on the property side, when we have a wind claim or a tornado claim, a lot of times when you see a structure that's collapsed in or fell in, it's automatic giveaway that you got to have an expert. Really, same goes for earthquakes here. If the building as a whole or any structure, the walls or crippled walls or columns are visibly out of plumb, if a wall and the flooring has been separated, if a wall and the ceiling has been separated, again, that's a telltale sign that you probably need to get an expert. If there's a pattern of splitting of framing members, whether it be hold-down locations, floor joists, etc., evidence of fresh settlement cracks or floors like you talked about when you talk about looking at your surfaces as far as concrete, hillside houses, things like that are obviously more prone to earthquake damage, and we need experts on those as well.
Absolutely. Just to touch on that, one of the more vulnerable areas are chimneys.
Yes.
On that. And, we won't get into coverage, but there's a whole section on coverage and how it's affected or how we can address the damage to the chimney. That bottom picture there on the right is a shake map. That is a tool, one of the many tools to use in evaluating these types of damages. Is you can go onto the site there, and whenever one occurs, there's a shake map that comes out, and some folks go in there, and there's a website provided, and they go in there and say if they felt it or not. And so you can go in there based on the epicenter where the claim is, and again, it's one of the many tools that we can use or we should use in evaluating our damages overall and see where, the loss location we're at compared to the epicenter of it. So
yeah, it's really along the same lines as running a weather report or a hail report. That tells you right there, were they close to the epicenter? Were they on the outskirts of it? How severe is the damage I'm potentially looking at?
Right. So we've got technical experts involved. So I think we've kind of touched on.
Yeah, a lot of this was on the last slide too. This is more of a reiteration. Let's go ahead and jump into the expert. I think we've talked a pretty good bit. Let's jump into Ron's presentation, see what he's got.
Having said all that, Ron Goth of Keystone Experts and Engineers, he's here with us today. He's going to present on causes of what earthquake damage looks like, of course, what it may not look like, and try to educate us on that. So,
Sounds
Ron,
good.
Are you with us?
I'm right here.
Hey, there you are.
Can you hear me all right?
We can.
Yep, we got
Thanks
you.
for
Excellent.
joining. So
Well, thanks for having me here today. This is a great opportunity, I think, for both of us. We get a chance to share some of what we look at when we're in the field from an engineering perspective, and maybe then help you while you're in the field, being able to determine what's going on in the field as well. So, a little bit about Keystone. We are a national forensic engineering company. We have been around for about 10 years now. We have coverage with engineering nationwide. We don't only work with engineers in engineering evaluations, but we also do fire, we do construction. We have construction experts as well. We can do all sorts of different things. We're expanding into some other areas as we speak. Part of what sets us apart from some of the other forensic engineering firms is we have industry-leading turnaround times. We're generally faster than just about anybody else in the industry. We're as or more accurate, but we produce that same product in a faster time.
Awesome.
We're technology-driven, so that tends to help promote those fast turnarounds. So. That's Keystone in a nutshell. A little bit about me. I've been with Keystone since 2018, right at 5 years now. I'm Director of Engineering Operations here. I graduated in the mid to late 90s in engineering and zoology. I'm licensed in 24 states currently, but I'm expanding that as we speak. I've done forensics for a lot of years. So I've covered just about anything that we see out there from a forensic perspective, from construction defect to fires and hurricane damage, tornadoes, hail, wind, light frame construction, heavy construction, industrial work, just about anything. I spent 10 years in the wood industry, so I've got a particular interest in light frame and wood frame construction, though that's not my only emphasis.
Mm-hmm.
All right, what are we going to talk about today? Well, generally, I'm going to try to touch on this from an engineer's perspective, from when you guys have already gone out there and looked at the property, and you've come and asked us to take a look at it and see what's actually damaged by the earthquake and what's been damaged by something else. So when we're doing that, the first thing we ask ourselves is, where was the earthquake, and how strong was it at the location we're at? But from an engineering perspective, we also need to know what the causes of an earthquake can be, and if some of those things are in the vicinity of where our building is. We also look at the movement that occurs during an earthquake, and what that damage looks like compared to different types of damage that occur from different types of movement. So today we're going to talk about what causes an earthquake. We're going to talk about what damage looks like to a building structure, because from an engineering perspective, that's most of what we look at is the structural damage. We'll look at the interiors as well briefly, and then we'll talk about damage that is often mistaken for earthquake damage, but really isn't. And I've got a couple of case studies that we can talk about, some stuff that we actually did here. So what causes an earthquake? This may seem elementary, but I think that this is some very good information. Michigan Tech states that earthquakes are usually caused when underground rock suddenly breaks and there is a rapid motion along a fault. This sudden release of energy causes seismic waves that makes the ground shake. An important thing to note here, I think, is that when we're feeling motion from an earthquake, we're feeling shaking movement side to side, lateral movement of the earth. We don't, the earth doesn't bounce up and down when there's an earthquake. It's always moving side to side, and that produces a specific type of damage in a building. What are the main causes of earthquakes? There's fault slippage that we just mentioned. There's induced earthquakes. These are earthquakes caused by human activity, tunnel construction, reservoirs being filled or drained, dams, geothermal or unregulated fracking projects. There's a bunch of stuff that went on with fracking in the 90s and early 2000s that caused localized earthquakes, but has since been regulated, so that helped. Earthquakes are caused by volcanic activity. We see a lot of that in places like Iceland and in the Philippines, where there's a lot of volcanic activity. We don't see so much of that in the United States, a little bit here and there. And collapse earthquakes. Collapse earthquakes are subsidence that occurs from, say, mining activity, underground mining activity, or if we end up with remote sinkholes, sometimes the ground can subside around that, causing localized earthquakes as well. So what do we use to measure the severity of an earthquake? There's really three scales that have been used. There's several more out there, but the one that we're probably most familiar with is the Richter scale. We always talk about that. That's always mentioned in television shows, but it's actually a bit outdated currently. This used a specific formula based on the amplitude of the wave action on a very specific seismometer, and the distance between the epicenter and that seismometer. Between the two of those, they were able to interpret a scale of 1 to 10 of what the extent or the intensity of that earthquake was. That had quite a range when you look at it from 1 to 4. I mean, they're saying 1 to 4 is a pretty small earthquake, swinging objects, feels like a truck passing on the highway outside, just very small vibrations. 4 to 5 on that was fallen objects, the broken plaster off of the walls, pictures falling off the walls, broken windows, those types of things. 7 is where you got into major damage, you get structural damage. And above that, you're getting into large bridges are destroyed, large buildings, and near total destruction at 10. The Richter scale, because of the specificity of the seismometer that was needed to measure the earthquake, it kind of fell out of favor in favor of some of these others that we're going to talk about here next. So the moment magnitude scale is one of the more common that is used because it's based on the total moment release of the earthquake. Now, when we talk about a moment from an earthquake perspective, we're talking about a force applied at a distance almost like a lever arm. And so the moment action that you see at a distance away from the epicenter. So forces applied at a distance away from the epicenter are measured, and that's how we end up with this moment magnitude scale. This, excuse me, this breaks down similar to the Richter scale, except that the numbers are different. So you end up with a 2.5 or less is generally not even felt. And a 2.5 to a 5.4 is the minor damage stuff. That's the plaster off the walls, the possibly broken windows, pictures come off the walls, that sort of thing. And then you get into some slight damage. The 5.5 to the 6 is very slight. This is potential racking in unsupported structures. You get displacement of interior walls and foundation elements for lighter and not properly designed structures. It's above 6 is where we start getting into significant damage. 6.1 to 6.9 is you see a lot more damage. You see racking of structures. You see collapsed and failed structures. Above 7 is where we get into significant damage to large areas of cities, large areas of rural districts, and beyond. So the third one that is often used is a modified Mercalli scale. This one uses observations of the people who experienced it. So it's a bit more subjective. So the amount of damage is that occurs helps to estimate the intensity. So this is subjective to the people that experienced it and the amount of damage that's observed. But it's still fairly widely used because it's got a good description of the damage that's used or that's observed. So when we look at 1 through 3 here, we're not hardly even recognizing that this is an earthquake. It's measured seismometeorologically. It's measured by the seismometers, and not even hardly felt by people. It's above 4, you're starting to feel it. You may see some things fall. There might be a little bit of shaking. 5 is where you start to see actual movement going on. Cars are going to sway, trees are going to move. And then above that is where we start to get into the more dangerous stuff, the structural damage and damage to buildings and other things like that. So any questions on that? That's pretty general overview. So we'll go on. Earthquake damage to a building. What does that actually look like? From an engineer's perspective, this is a great little video. It shows shake tables that are used to simulate earthquakes. And the great thing about this is you get to see how buildings actually react when they're being shaken by an earthquake. Something I want you to notice on this one is the building on the right starts to fail, but on the lower level, but you don't see any failure above that first level. And that's because the earth is shaking beneath it. You're not getting any kind of wind action. You're not getting any kind of movement of the building above that, except what's being caused at the ground level. We've got a few of these that show that actually pretty well. This one's actually another one that's really good. Another thing to note on these is these are being shaken in almost a circular pattern. And there's some of them actually just go back and forth, right to left. But these are actually pretty good simulations of what actually occurs with an earthquake. And you'll also note that all of these fail at the ground level. They usually fail right at the connections near the bottom and due to the shear wall failure. We'll talk about shear wall failure in a few minutes from an engineering perspective, but let's skip ahead here. You've probably seen buildings that are built with these cross diagonals as opposed to shear walls, sheathing that's placed on the exterior or at the corners of these walls. And you can see here that they don't seem to hold up very well. there's a better one a little bit further down the road here. The great thing about this video is this shows 3 different types of construction right next to each other. And this is the one we just looked at with the diagonals here on the bottom left. On the right, bottom right, it shows diagonals in cross bracing to strengthen the wall in both directions. And then on top, we see actual shear wall construction with sheathing. And you can see how they hold up under the same conditions. The one on the bottom left starts to break almost immediately. The one on the left or bottom right is still swaying pretty good, but it's holding up much better. And then the one that was on the top there, once on the top there, is hardly moving at all. Shows you the strength of those types of different types of construction. I think that's about all I've got on this one. This is a great one. Unique construction techniques that have been tried over the years. The Japanese tried for a while to avoid connecting the buildings directly to the foundation, because they found that if there's movement and if the building is allowed to move across the foundation, it'll actually the foundation can move and shake and it won't damage the building. Didn't actually work because the construction techniques don't allow for that, but it was a great thought to begin with. Sorry, by the way. So from a residential building perspective, let's get back into our full page here. From a residential building perspective, the main types of failure that we see are racking of the structure. We see foundation failure, and then full-on collapse of the building. So one thing you guys, I think was mentioned earlier, was this X shape damage that you see from shaking of a building. If you remember back in the video, we saw the X-shaped bracing significantly held up compared to just one side bracing or just one diagonal in comparison. And that's because of the way that these shear walls act. We're going to talk a little bit more about shear walls later, but when buildings are racked, when that bottom portion of the building moves and the top is allowed to then flex, you see this movement where the building shakes and moves laterally back and forth. And this causes a stereotypical X shape in the failure of the brick. And you can see that over here on the right-hand side. There's an X shape that is very present in this failed brick veneer on both sides and even on top up here. And if you look on the left, you can see that one between the fenestrations. That's really quite common. The one in the center is actually a bit of a trick. That one's not caused by shaking of the building. This is a vertical crack through here. This one is more likely to be settlement or shrinkage cracking, depending on the overall condition of the building. So racking of a structure, this is very similar to what we saw in the video, but you can see that most of the damage occurred at the ground level story, because that's what's shaking, that's what's moving, and that's where the failure occurs in the shear walls. The upper portion of this building is mostly intact and only failed after the building started to rack and collapse. Foundation failure. Foundation failure, when we're looking at that from an engineering perspective, we're looking at horizontal cracking with diagonal, radiating cracks in the masonry here. If we're looking at concrete, we're looking at almost circular or arcing type cracks. So what we call a bending failure. So we get when these things bend from settlement or from lateral displacement, you can see these cracks are in almost a circular type of pattern there. And of course, the columns above that are above ground, you see failure like that quite often, similar to the same action that we were seeing in shear wall failure. The ground is shaking and the columns are kind of going in an opposite direction of that and end up failing like this. Different types of foundation failure. And then of course, collapse. Overall collapse of the building usually occurs due to a failure of one of the other two. We either see racking failure, which we're seeing in the bottom right, which caused failure of the first level story, or the first story of the building, and then collapse of the rest of the building. We're also seeing similar problems in the center there, but on the right, we're seeing failure of the structure of the wall, not of the foundation or necessarily of in a racking failure. This is just more failure of the wall that resulted in collapse of the supported elements. So any questions on that? No questions yet. We'll keep moving then. Earthquake to interiors is a little bit different, but not significantly so. We're going to continue this discussion about our shear wall and what a shear wall is and how it fails. On the left there, shear walls are designed to withstand lateral forces that are applied. This was originally started with wind damage. So you'd see wind on a structure that wasn't really very laterally supported, and the wind would just cause these things to topple. So when you apply a force, if you look at the left photo here on the right portion of the left photo, you see that this is, if you apply a lateral force at the top of this wall, you're going to get this lateral displacement and creates like this parallelogram sort of appearance, which if you remember the video, that's exactly what was happening to those walls. And if you provide lateral stability in the type of in the form of a shear wall, then this shear wall helps to take up that force, that lateral force, and it will transfer that back down to the ground. We see the same things in concrete and steel construction, because in steel construction, they'll make X's throughout, which we've seen has to be very stiff in order for that to act as a shear wall. But in concrete structures, we'll make the shear wall full depth, tie that all together into one large panel, and we'll do it in both directions. Oftentimes these take place or are constructed within the elevators, elevator tunnels, or the stairwells. Oftentimes those are where we transfer the loads to take up that kind of shear wall loading. On the interiors of a building, I want you to still picture that when the building racks, when it's laterally pushed horizontally in opposite directions, we end up with cracks that are primarily horizontal in direction. Like this bottom left, this is a classic horizontal fracture failure, lateral racking of the building, and shear wall failure. The same thing on the top here, because, or in the center. These are fractures that are primarily horizontal, but have failed in other directions as well, because if you consider a building or a wall that's actually racking, you're going to get multiple shear failures in the wall. The stair step here is a shear wall failure in a masonry wall, and we usually see these with large separations, not just the stair step cracking in there or diagonal cracking, but you'll see these large horizontal separations as well on the interior brittle finishes. The other thing that we see are uneven floors that occur. This occurs for a couple of different reasons. If you get shear wall movement, failure of the wall at the foundation level, then you can get displacement of that wall that causes buckling, like we're seeing in the center here, buckling of the floor finishes and the floor itself. On the left, we're looking at failure of the subsurface of the soil due to the shaking of the earth. We usually see this in hillsides where the soil is not completely stable to begin with. And we're talking slab on grades. We're also talking about foundations and slab on grade stuff that has improperly or inadequately compacted. But we also see it in areas where there's just a groundwater table that can pull some of the soils, some of the fines away from the building. And then when the ground shakes, then you get very quick settlement of the soil beneath it. As I think it was mentioned earlier, soil composition is actually becomes fairly important when we're looking at uneven floors and failure of the floor systems. So moving on, damage that's often mistaken for earthquake damage, but isn't. I was looking for a photo of a collapsed building that had collapsed due to something other than earthquake, and you might see here this is a sinkhole. This is obviously not an earthquake, and I don't think that anyone would mistake this for an earthquake, but it was a photo of a collapsed building that I thought looked cool. So damage that's often mistaken for earthquake damage are vertical foundation movement. As I was saying before, the only time that we do see vertical movement is usually in slab on grade type foundations. And then you get soil movement, localized soil movement that causes failure of that slab. We rarely see it in vertical foundations, stem wall type foundations, or in deep piers. The reason for this is the soil is much deeper, it's usually better compacted, and we don't see vertical movement of the foundation as much because, again, the movement of an earthquake is horizontal, it's not vertical, so we don't see any kind of bouncing. Vertical foundation movement is rarely caused by earthquakes. Shrinkage cracks are often mistaken for earthquake damage. A homeowner will say that all of these cracks on the interior and in the brick exterior were caused, or they weren't there before the earthquake. So you go and you start looking, and it's like, well, they probably just didn't notice them because they're old. They may be diagonal at the corners, which is indicative of differential foundation movement. And interior finishes tend to, over time, separate due to differential shrinkage. So you might see a separation between the baseboards and the drywall because they're moving at different rates because the materials are different. Those are the kinds of things that we see. Of course, shrinkage and cracks in concrete, as we all know, is very, very common and can occur even years after the concrete has been placed. And binding doors, that's another one that we hear a lot of from engineers. From an engineering perspective, is we go in and they'll say, yeah, these doors after the hurricane or after the earthquake, all the doors started binding. And then you get to looking, and you see rub marks, and these things have been binding for a long time. There may have been interruption of utilities that cause them to swell from humidity level changes, things like that generally are much more common. We don't see isolated displacement of a fenestration without damage to the wall around it. You might see an exterior wall or an exterior door that binds after an earthquake if the exterior structure has also been racked and there's indication of that. But the local fenestrations don't move on their own independent of the exterior walls or the shear walls around them. So any questions before we get into the case studies? This is the good stuff.
Hey, Ron, can you hear me?
Looks like we're not getting any questions yet. That's great. Go ahead. All right, case study. First one here, in this particular building that we were looking at, this building was exposed to a 5.7 on the moment scale. And if you remember, that scale said that that's strong shaking with potentially light damage to structures. Some of the things that we did see in this one that we attributed to the earthquake was the large crack between the kitchen and the living room on the interior of the building, and some horizontal cracks in the finishes on the exterior walls. And I'll show you those in a second, why those two are different. But there was a lot of damage that was not associated with the earthquake in this case. There were a lot of miscellaneous cracks on the interior finishes and walls. There was siding that was displaced on the exterior, and the garage doorway lintel. They were claiming that the lintel had deflected due to the earthquake, and I'll show you that in a minute, but it was not from the earthquake. So this is the stuff that we saw that was actual earthquake damage. Excuse me. This vertical crack, pardon me, this is on an interior wall. So this particular wall was being twisted rather than racked horizontally. So you could see that this wall had moved in kind of a twisting motion as opposed to a lateral sort of rocking motion. And that's evident in this wide crack in the finishes here. And this central wall that we're seeing here in the central photo, the blue wall, this is a crack on the other side of that same wall. So this is an interior wall, but it's also functioned as a partial shear wall because of an addition that was added to the building. But the point of this is that this wall was twisted rather than shaken horizontally. And then we look on the top on the upper right, and that's a classic horizontal fracture from racking of the exterior wall. So I'll put all of those together and you're getting racking of this structure in a very light sort of manner. And we're not seeing significant damage. We're not seeing large separations of this crack. We didn't see a significant number of these cracks at the fenestrations, just in the areas where the shear wall capacity was the smallest, meaning it had the largest fenestrations, the largest openings in the walls, so it produced the weakest shear strength. The stuff that we saw in this one that was not due to the hurricane were cracks. This is shrinkage cracks. This is between the backsplash in the kitchen and the baseboard here of the countertop. We get some shrinkage cracks and some settlement crack going on there between the different materials. There was some separation in the vinyl siding that they were claiming was from the hurricane or from the earthquake. You can see that this has had some shrinkage in this caused deformation here. And this is just some movement of the vinyl trim at the edge, but no real damage there from the earthquake. Now let's go to the bottom first here. This one, or the CMU wall, had some cracks in it that had been repaired. So this was obviously predated the earthquake. And there are some additional cracks going on here. So this was more settlement issues. But when you look at this lintel here, you can see some deflection across that. Right near the center is where it's the greatest. But when we looked at that closely, there were almost no cracks in that at all. This thing had deflected or had been built that way. Most likely the bond beam that they created to create this lintel, because there was no steel creating the lintel, it was a bond beam in place, was likely under-designed. And when they removed the shoring from building that, it probably just sagged before it was fully cured. So that's what we found on this one. Any questions on that case study?
Hey, Ron, can you hear me?
Yes, I can.
Hey, sorry, I saved all my questions for towards the end, but on that particular case study, I just want to go back to what you had mentioned. One of the things, the CMU wall, with the vertical crack there. I mean, that's, like you said, that's not earthquake related. That's just settlement,
Yes.
and shrinkage going back and forth. So I could see how, not knowing any different, why, if you've had an earthquake, that may be, is it related or is it not? But again, you touched on that and kind of the binding doors. There's going to be collateral evidence to support, the adjacent wall or the supporting wall to it. So not really a question, maybe a comment.
Yes, you're absolutely right. We're often thrown a few pictures, maybe 2 or 3 pictures, and say, is this earthquake damage? And from an engineering perspective, that's something we can't answer. We can say, well, maybe, because we always want to take a look at the whole picture. We don't want to make a determination just based on a couple of photos. We want to look at the whole picture. We want to look at the building as a whole. Was this an exterior wall? Was this an interior wall? Was there evidence of racking of the structure or twisting or displacement on the exterior walls before we started looking at the interior walls? We want to look at this from a whole building perspective, and sometimes even surrounding buildings and surrounding area to get an idea of what kind of damage occurred before we even make any kind of determination. So yes, you're absolutely right. There's going to be collateral damage near there, and if there isn't, then we tend to lean toward other types of or other sources for the damage.
Right. Yep. Good stuff. Don't let me hold you up.
All right, so next case study, this building, and I think this is going to also illustrate a little bit about some of the things that we see out here. But when we were looking at this one used the modified Mercalli scale. When we were looking at this one, it rated a 7.3. That's the one that's based on observation and damage rather than on any kind of measurement. This one is described as very strong shaking, moderate damage to structures. And when we were out there, there was definitely some structural damage to this property, but there was also some construction defect associated with this property. And I'll get into that a little bit more in detail here in a minute. But there was displacement of the brick and stone chimneys. One of the support posts at the edge of the footing on the back of the fireplace. I'll show you that in a second, but instead of having a foundation around the fireplace and the hearth, they simply put wood braces to support the hearth and the fireplace on the interior. And a couple of those fell during the earthquake that caused subsequent damage based on the construction defect and, of course, the shaking. There was siding at the front corner that had been shifted. There were interior wall cracks. There was damage to the siding of the front entry and stucco. Those two last ones were due to another construction defect, but was also ultimately caused by the earthquake. If the earthquake hadn't occurred, the construction defect wouldn't have caused the damage. It was just a defect. There was some stuff, there was separation of the stone, the upper portion of the chimney that actually was not caused by this. It was an ongoing problem. And there was some flatwork separation and vertical foundation cracks that were not caused by the earthquake. Let's take a look at some of this stuff. You can see on the left there's significant displacement of the chimney. It's a lateral displacement that's consistent with with earthquake movement. We have new fractures, we have wide fractures, we have offset fractures. All of that is consistent with shaking and displacement from earthquake. I'll come back to this one in the center in a second, but actually let's move on to this one. This one is what I was talking about before. This is near this area behind the 2x4 that's sitting there is where the fireplace sits on the foundation, where the chimney, I should say, sits on the foundation. This 2x4 is supporting the hearth directly above, and it's sitting on a little post here. This was moved. You can see there's bright wood here, and there's an outline of where this thing had been sitting prior to the earthquake. And when this thing moved out of place, I don't have a picture of it, I guess I did it to show here, but the hearth dropped and caused damage to the hearth there, and it was bright fractures in the stone, very obviously recently occurred. So we attributed this to the earthquake, but had this been built properly, who knows what would have occurred. This bottom right-hand photo here shows two 4x4 blocks that are placed here supporting the wood framing directly above. And during the earthquake, these buckled out of place, shaking back and forth. And that caused the fracture that we're seeing here in the stucco directly above. It caused the bump out and displacement of the siding adjacent to it. This is just general wood framing that was, very poorly done, and allowed for this kind of displacement from the earthquake. But this we attributed to the earthquake itself. Stuff we saw that they pointed out to us that they thought was from the earthquake that wasn't includes, this is the stone chimney. And if you go look up here where the tarp is where the chimney, the stone portion of this chimney was located. And they had ongoing separation going on here. This has been a long-term problem. And that's consistent with earthquake because this movement is near the earth that we were showing within the video. You're seeing lateral movement and the top kind of holds its own and kind of stays there. And that's what we saw in this case is once the chimney portion displaced and broke here, it continued to move and the top didn't. That's why we end up with this being an old condition. We had some separation between the flat work, which, you know, we see this all the time, and that's just general settlement and differential shrinkage. And then we're seeing a fracture in the foundation the slab that is an old crack that in a vertical crack in the center area with no collateral damage around it. There was obviously just a shrinkage or settlement crack. So I think I'm under time, or at least I'm close to under time. Ready to take any kind of questions, anything or any comments or anything anybody has to say.
Yeah,
Murphy, we got one.
Yeah, I actually had a question specifically about the case studies and properties if you've gone out and visited and things like that. Have you ever had one that is like super late reported, like an earthquake from months and months? I think of earthquake, damage in terms of it just happened. Policyholder files a claim, expert comes out and looks at it. Have you had one that, maybe the damage occurred months and months ago, but now it's gotten to the point where it's caused residual damage? Have you seen that?
We have. Usually these things occur when someone feels a shake, they don't see any immediate damage, so they don't file a claim.
Right.
Months later, they start to see foundation damage, settlement, cracks, binding doors, movement in the house that they're saying, geez, I wonder what caused this. Well, we had that earthquake 8 months ago. Must have been this as a cause. Yeah. So we do see that a bit. I can't say that it, specifically what caused it, what always causes it, but very frequently these are long-term conditions that were only noticed after the fact. Right. Rarely do we see latent problems in a foundation or in a building that only appear months later.
Gotcha. That
can occur sometimes on pier foundations. If the piers are exposed above the ground, because you can get some shaking and some movements that causes some radial cracks and some fractures within those piers that then only later start to develop. You might see oxide jacking of the steel inside of it, or you might see spalling of the concrete off of those piers. And that's something that can be experienced, months or observed months after the inspection or the earthquake itself. Yeah. But in most cases, those are we don't see latent damage from an earthquake.
Okay,
good question. Very good question. We got any more that may have popped up?
Yeah. Another question. We had a claims corner. I guess it was probably about a month ago. Yeah, it was probably about a month ago on fortified homes. Have you ever consulted or inspected on a fortified construction home, and how does that differ? How do they hold up, I guess, as opposed to your standard home?
When you're talking fortified, you're talking retrofitted for earthquake itself?
Right.
Okay. Yes, I have personally inspected a couple of those, and surprisingly well. It depends on the methods used. So if you've got a building that didn't have shear walls, for example, and only had diagonal bracing, and they went in and retroactively put shear walls maybe on the interior before they put their drywall up. Now you're creating a very solid shear wall capacity. the question comes is, did they also fortify the connections at the base? Did they fortify the connections at the top of that first floor? Simply the application of a shear wall is going to significantly improve the performance of the building, but it's not necessarily going to improve the performance of the overall build, of the overall structure. So the question is, a typical engineering answer, maybe. Yes, there are parts of that are definitely improved by the retrofit, but it also depends on the construction techniques, how well they did the construction, and how extensive the construction was.
Gotcha.
I've got a couple of quick comments before we wrap up, just to go back to what you were before the case studies, and some of the photos were in the case studies, but the modified scale, it's interesting to me, is uses the observations of those who may have experienced the earthquake and the damages they may have to determine the intensity of it. The videos that you showed with the different construction, the way they were built, really kind of made it easier to understand, I guess, if you haven't worked an earthquake claim before, it kind of give you an idea of how that, like you've mentioned it before, adapt to it, or how they react during the earthquake. The settlement shrinkage thing, especially on the interior. I know you mentioned the brittle finishes, are usually an indication visually. I know over the years, for example, I'll give you an example, real life example, replacing the flooring in a room. In my parents' home, pulling up the carpet, and you look down and you see the crack in the concrete. I mean, that's just over time, right? It's not, if that's just isolated to that, where is the supporting evidence, the collateral? So that's just my comments. As far as the information you provided, I know very informational, good stuff to remember, and key takeaways. Craig, are you still with us? Is the heckler still out there somewhere?
He's not on. I think we kicked him out.
We kicked him out. Good. Okay. But that's all I have. You got anything to add?
No, I just want to obviously extend a big thank you to Ron again for joining us today. This was great stuff. Appreciate you having me on again as well.
Absolutely.
It means a lot. Yeah, really good stuff today.
Yeah.
Well, thanks for having me, having us as Keystone. This is, like I said before, this is always a great opportunity for us to be able to share our perspective, and to different audiences. So this is great. We really appreciate you having us.
Yeah, and and when is earthquake season?
Anytime.
Every day, right? Every day. All right, Ron. Thanks again. Just before we go, want to thank everybody involved behind the scenes, our media team, marketing team, for putting this together, and everybody involved. For those that can see, and 2 weeks?
Yep.
Is our episode 6, 7?
Yep.
7th one.
Be episode 7.
There we go.
On May the 11th. Yeah.
Repairability versus replacement, and the roof snake use. That's going to be interesting. And Knights is going to partner with us on that one. So be sure to sign up for that if you hadn't already, and join us, and we'd love to see you. So with that being said, thank you guys for attending, and we'll see you in 2 weeks.
See you, everybody.
Thanks, guys.
Yes, sir.
This is my first year working for CNC, and it's been a great experience. I've had so much support and so much training through so many different people at the company. If there's one person who can't help me right away, they'll get me to somebody who can, and that's been the main reason why I've wanted to stick with CNC this year, is because of the amount of support that they've provided, and they're really helping me excel.